That's good. My name is Hayden. I'm co-president of Student Energy Club. And we have one of the most knowledgeable people of all time, no pressure. Nuclear power, John Zino. He works for GE Hitachi and is a associate professor here, teaching Monte Carlo and things that go way above my pay grade. So, don't tell him I said that because I'm going to take that class later. But yeah, so he's going to speak to us about low introduction nuclear technology, its history, talking about how it works and what it's like right now. So, warm welcome to the man.
Hey, well, appreciate you having me here today. Going to ask that you maybe try to excuse my voice a little bit. So I'm still recovering from a little bit of a cold, and the allergies seem to have gotten a hold of me here recently. But make sure this works here. Let's see how this does.
Excuse me, it's not sharing on Zoom.
Oh, not sharing.
Not
Okay, all right.
Sorry to interrupt.
Well,
No, you're good.
They can see the slides all right.
Oh, okay.
It's like,
Again, okay.
Yeah.
Okay, so I guess what I want to talk about today, I'm going to try to keep this about an hour because I know that pretty close time limit. So as Hayden said, I do work for GE. I also teach here at NC State as a teaching professor. And so I've had opportunities to interact with a lot of folks in the nuclear industry as well as in the university and academic setting. And so what I wanted to try to do today was just give you a little bit of background on nuclear power. Now, I know this is Energy Week, and we're talking about lots of different types of energy sources and energy power sources for current day and for future. And so my goal today is to try to convince you, hopefully successfully, that nuclear power needs to be part of that energy future discussion when we look at goals that we're trying to reach from a net zero carbon emissions perspective, carbon reduction footprint. We recognize that I think nuclear, along with other types of renewables, has to really be part of that solution. So we put together this presentation years ago for folks that were new to the nuclear industry, who maybe have a little bit of background about nuclear, but not a whole lot, just to give some context around what is nuclear power, how does it work, why is it important, what are the risks? I mean, there are risks with everything in life, right? So we need to understand those risks. And then what does it look like going forward in the future? So that's kind of the roadmap for today. Like I said, I'm going to try to keep it at about an hour, and hopefully we won't go longer than that. So I'm going to forward that. Oops. See if that's working. Maybe not. Okay, I guess I got to get over that. Okay, so I'm going to do a brief history of nuclear so that you kind of understand some contextually how we got where we are today, and then what it looks like today, and hopefully what it looked like in the future as we go forward. So I'm going to start. Yeah, go ahead.
I'm going to try to share the slide again.
Oh, is it having a problem? All right.
Sorry to interrupt.
Okay, yeah, you're good.
I'll unjump.
No, you're good. It's just not showing that. Okay. Try that.
Okay.
There you go. Okay, is it going? All right, good. Okay, so talk a little bit about the history of nuclear. Some of you may be familiar with this, some maybe not. We'll kind of go through it pretty quickly, but I think it's important to understand sort of the history of how we got here. So in the 1920s and 30s, in the US and in other countries around the world, there was significant interest in understanding the structure of nuclear matter, atomic structure of matter. There were a number of scientists working in a variety of countries and different laboratories trying to understand the behavior of the nucleus of atoms. We understand at this time, we understand sort of the chemically how elements work, periodic table, chemistry, but we didn't have a lot of understanding about how the structure of the nucleus and what makes different nuclei different than others and why that's important. And so in the early 30s, there were a number of scientists and researchers who looked at the nucleus of certain elements, especially the heavy elements like uranium, and started to notice some interesting features about these heavy metal atoms. In particular, that it seemed, at least the theory predicted, that they could split and release energy. and also release subatomic particles at the same time. And so there were a number of researchers that were looking at this new scientific discoveries that were being uncovered. Oop, wrong way, sorry. Going the wrong way here. There we go. And like I said, in the 1930s, mid to late 1930s, there were a number of researchers in Europe and in the US who were looking at this. And these are just some of the famous names that you may have heard of. Enrico Fermi, Niels Bohr, the Bohr model of the atom. Maybe that's familiar to some of you. You're taking chemistry. Lisa Meitner, Otto Fritsch. A number of scientists were looking at the atomic structure of some of these heavy elements. And in 1938, interestingly enough, a couple of chemists in Germany discovered that uranium had some interesting features such that if you were to shoot neutrons at this atom, that it would actually split and release energy and release other neutrons. They identified fission fragments. They call this process fission because it was like splitting the atom apart, splitting the nucleus apart. And the experiments were fascinating if you read some of the literature. So they would take a small foil made purely of uranium and they would fire neutrons at it. And then they would chemically analyze the sample. And when they did, they found that there was uranium there, but there were also a bunch of others that were not part of the original sample, like cesium and strontium and iodine. And it completely baffled them because where did all these elements come from if they weren't in the original sample? How could just shooting neutrons at this target produce all these other chemical elements? And what they were discovering were fission products, fission fragments that were the result of the fission process. And in fact, Lisa Meitner, Otto Fritsch formulated the liquid drop model of uranium for nuclear fission and actually confirmed Einstein's prediction that what was actually happening was that the atom was splitting, releasing energy and causing these fission products to be produced and trapped in the sample. And so this got scientists and engineers very excited because they realized, wait a minute, if we can do this on a large scale, I mean, this was just a small scale with just a small sample, but if we could get enough of this uranium together in a certain orientation and a certain configuration, and neutrons are being emitted as others are being absorbed and fissioning the uranium, could we actually create a system where this fission process could self-sustain, where it could just kind of run on its own? Because as the fission process happens, more neutrons are emitted, and those neutrons can cause further fission. And in fact, that's what the researchers at the University of Chicago, 1942, Enrico Fermi, what was really the start of the Manhattan Project, began to do. And they actually assembled a large, and you can see the picture here, a large block of graphite, a large pile of graphite blocks. And it was actually called a pile. It was called the Chicago Pile 1, CP1, that had uranium spheres lodged in the middle. And as they stacked the blocks and added more uranium and more graphite, they began to see that they could achieve, under certain conditions, a self-sustaining chain reaction, which would produce a very, very low but steady power level in the reactor pile, in the reactor core, what we would call a core today. This was the first artificial nuclear reactor ever created by humans. And this led to thinking that said, hey, maybe we can actually use this for a number of different purposes. Now, obviously, 1942, you have some idea of what was going on back then, right? In world history, we were in the middle of a world war. So clearly there was some interest in using this technology for a weapons application, but there was also use for energy production as well. And in fact, that's exactly what happened. After the war ended, the US, recognizing the significance of this technology, formed the Atomic Energy Commission to foster the peacetime control and use of atomic science and technology, primarily for non-weapons or military purposes. And now there are a lot of areas where nuclear technology can be applied outside of a military or weapons environment. And so this was formed to be an energy commission to try to figure out how to harness this thing called nuclear fission to produce energy as a power source. And in fact, in the early 1950s at Idaho National Lab, a small nuclear reactor was built, only a few hundred kilowatts, that produced electricity that was used to spin a turbine generator and actually produced enough electricity to light up a small number of lights. And actually they were able to raise the power level to light up a small town in Idaho called Arkville, Idaho, that provided electricity to a power grid for electric consumption, for commercial civilian use. And so this was really the first time in the US that we had seen this capability to be able to use this nuclear technology to produce electricity. From this point in the 50s, in the 1950s, you started to see rapid development of nuclear power for energy production. The Soviet Union was the first to build an actual power station for civilian purposes, 5 megawatts, so that's 5 million watts, which is extremely small by today's standards, but was enormous by the standards of the day, producing electricity for civilian purpose. Our friends in the US Navy thought this could be an interesting way to power a submarine, because after all, submarines prior to this had diesel engines, which needed oxygen, right? So they could only surface at night to run their diesel generators, and then during the day they had to go under the subsurface and run on batteries. Well, guess what? Here we have a combustion. Here we have a source that doesn't require combustion. It can produce a lot of power, a lot of electricity, and you can actually use it to run a submarine underwater for months and months and months at a time. So nuclear power revolutionized the naval submarine force for the US and for other countries, because the boats could stay underwater for a significant amount of time. In fact, the story I've been told by some of my colleagues who were in the Navy is that the most limiting factor on a submarine is they run out of food for the crew. So they have to come back and put more food on the ship for the crew. That's how long these things can run underwater, for literally months, if not years at a time. So it's really fascinating to see how the deployment of the technology really started to take shape. In the late 50s, commercial companies like General Electric and Westinghouse began to look at this as a possible way to commercialize the technology for civilian nuclear purposes. Out in Northern California, north of San Francisco, the Valecitos laboratory built the boiling water reactor, the world's first privately financed nuclear facility, and actually had the first license to operate a civilian nuclear station in the US. Westinghouse had a lot of significant contribution to the Shippingport power station in Pennsylvania. Now you can see the power levels are getting up quite high. Now we're up at 60 megawatts electric, which is about 180 megawatt thermal. So you're starting to see the power levels scale up pretty significantly as the technology is maturing and developing. And so commercial companies start getting involved in the development of nuclear power. When this happened, things really started to explode and boom in the industry. From the early 60s to the late 70s, early 80s, you saw a rapid deployment of nuclear power across all sectors, not just in the US, but across the world. And you can kind of see the ramp, the increase that took place as new power plants were coming online very rapidly. And the installed base of electric power was increasing tremendously from less than a gigawatt to over 100 gigawatts, which is an enormous amount of electric power. And you see it starting to plateau around the 1980s. And it's been relatively flat in the US since then. Other countries like China have now starting to see an increase with new nuclear builds in China the last 20 years. But this is the history of up until about 2005 as you started to see new deployment. With all this commercial and civilian nuclear deployment, the US Atomic Energy Commission actually divided into 2 branches. So they became 2 separate organizations. One was the Nuclear Regulatory Commission, which regulates civilian, non-government use of nuclear power, as well as radiation sources, radioisotope sources. And then the Department of Energy, which handles all the government related, which is usually the national labs and defense programs, are all handled under the DOE. And there are a number of national labs that run under the DOE, and the civilian nuclear is entirely separate. They run under a license by the NRC. And so this really is when things started to really mushroom for the industry as the commercial nuclear industry began to grow tremendously. Probably some of you have heard of this. 1979, there was a partial core meltdown at 3 Mile Island, which was a pressurized water reactor. This was through a number of operator errors as well as mechanical equipment errors that caused part of the fuel to melt. Fortunately, because of the containment and because of the vessel, there was minimal, if to none, no release of any radioactive elements out off the site boundary. Everything primarily stayed contained inside the reactor vessel. A lot of great lessons learned from this event. And what we started to see in this time in the industry was utility companies that had these power plants didn't always share information with one another because there were commercial advantages to, like, if you found a really good way of operating your plant and made you more efficient and more cost effective, you were sometimes reluctant to share that with other utilities because you wanted to remain commercially competitive, especially if you had like a merchant plant that put energy on the grid at a commercial price. But what we started to realize, what started to happen was, in 1979, the civilian industry recognized the need to start sharing more public information about nuclear power operations, recognizing that safety really is the key overriding priority here, especially when it comes to nuclear technology. And so the Institute of Nuclear Power Operations was formed in 1979 so that utilities and industry partners could begin to share information and benefit from lessons learned and operating experience. As it turned out, the 3 Mile Island event that occurred in '79, there was a not identical, but a similar near miss that had happened about a year earlier at another. And had that OE been shared, had that operating experience been shared, it's possible that that event might have been avoided. And so I think this was really a transformational point in the industry history, because it started to drive home the fact that we need to share this information with one another. And INPO does that in a very effective way. And so all members, all utilities in the US that have power plants are members of INPO. The vendors that supply equipment are part of INPO, so that there's sharing all throughout the industry. In 1986, unfortunately, we recognized that maybe some of the lessons learned had not always been shared outside the US. And an unfortunate event happened at Chernobyl reactor number 4, which was a plant that was a significantly different design than any of the plants we have in the US. It was a very old style reactor built in the early 50s that did not have nearly the number of safety controls and features, and nor did it have a containment around it, like all of our plants are required to do. A significant reactor power excursion occurred, a steam explosion, and considerable release of radioactive material into the environment. Arguably, I think most would agree, probably the worst nuclear accident to date that has ever happened. As a result of this, all of the world nuclear operators recognized that we needed something like INPO, but for the entire world. And so the World Nuclear Association, WNA, was formed a few years after this in 1989 to do just that, to be able to allow international power plant operators to share information to help to avoid events like this in the future. So we've been learning as we've been going, and we've had a number of, I think, even though we've had some near miss events, they have been indications that we are becoming a very good learning organization, and where we're heading off problems before anything really becomes a significant issue. In 2002, Davis-Besse, a plant in Ohio, had significant degradation of the vessel head. And thankfully, with some good questioning attitude and some good root cause analysis, it was a significant event was avoided because they were able to detect operating experience to help the plants run safer and more effectively. In 2011, through no fault of their own, the people running the Fukushima plant, the units in Fukushima, were greeted by a 50-foot wall of water that crashed into their power plant after a tsunami as a result of an earthquake in the Pacific Rim, causing pretty significant damage to several of the reactor plants in 2011. Again, natural disaster, no operator error here, but still a significant event for the industry. And we've had a number of lessons learned that have come out of this as well, in terms of redundancy, of off-site power, to help plants be able to recover from some catastrophic event like this. So we've had a lot of learning and a lot of history that we've been able to share over the years. But that's kind of a brief overall history of just some of the really highlights of nuclear. Any questions on any of that before we go on? I want to maybe give just a minute if anybody has any questions.
So just to confirm, the DOE then oversees Burlington here on campus?
No, that's the NRC, because that's a civilian.
Oh,
it's a civilian. Yep.
Okay.
Yep. So that's a good question. So yeah, so the little test reactor we have here at NC State, really cool, by the way. If you haven't seen it, go see it. It's pretty neat. That is run under license to the NRC, right? Because it's not a military, it's a civilian use, right?
Okay.
So yeah, no government involved, no government money, no government funds. It's run as a commercial operation.
Okay.
Yep. Good question. Yeah, good question.
I have a question.
Yeah, yeah.
The World Wide Organization for Operations.
Yes.
Does it involve, as saying for some people like, hey, you are not allowed to build a nuclear power plant for such a reason, or it's only focused on operation?
It's only focused on operation. The group that would be involved with what you talked about is the International Atomic Energy, the IAEA. They're more concerned with those kind of considerations, especially if they have to do with weapons proliferation or weapons dissemination. But info and WANO are just for operations, for people that have existing power plants that are operating. Yeah, good question. Good question. Okay, all right. How are we doing on time? I'm doing the time check here. I don't want to run too long. Okay, we're doing good. So I want to spend a couple of minutes digging into a little bit of the technical details now. So I apologize up front for those of you that maybe get a little freaked out when you see the periodic table. So I gave this talk once to a group of folks in finance, and literally the minute I put this up there, you could just see this collective sigh from everybody in the like, oh, I thought I'd never have to see the periodic table again. So uranium, I've been talking about uranium. There's nothing really particularly enthralling or magical about uranium. It exists naturally in the Earth's crust. It's a metal, just like any other metal. We mine it out of the ground, just like we mine copper and silver and gold. There are uranium mines out west in the US. Countries have uranium mines all over the place. So it's a commodity. It's just like any other precious metal. It is a very large nucleus. It's what's known as the actinide series. So it's got a big nucleus, 92 protons, and the number of neutrons can vary depending on the isotope. The one that we're interested in is really U-235, which actually is a very small percentage of naturally occurring uranium. Most uranium in nature, about 99, a little over 99%, is actually U-238, which is by and large, I'm going to say neutral. It doesn't really contribute anything significant to what we're interested in for nuclear fission. It's the U-235, the one that we want, because that's the one that is fissile and fission with neutrons that will allow it to produce electricity, power that can produce electricity. So while the natural enrichment is a little less than 1%, we generally need to get the uranium enriched to at least a few percent in order to actually use it in a reactor, in a power plant. Most commercial reactors are licensed up to about 5% enriched. There are some special reactors that are enriched higher than that for particular applications. Naval reactors are much higher than that. But by and large, most civilian plants are right around the 5% enrichment level. And uranium, as we said before, has a lot of interesting attributes, even though it's something that gets mined out of the earth. It is naturally carcinogenic, so you have to handle it carefully. But you know, benzene is naturally carcinogenic, right? So, I mean, it's not the only thing that's naturally carcinogenic. It is naturally radioactive. It does emit very, very low levels of radiation that can be handled and shielded very safely when taken out of the ground. It is fissile. It undergoes fission. It undergoes that fission process, which is what we like because we want to be able to utilize it to produce power to produce electricity. And as I said before, it is one of the key isotopes that we use in nuclear power. I won't go into the other ones, but it's the key one for our purposes. And this map is a little dated, but you can kind of see where you can find natural uranium reserves around the world. The United States we actually have a fair amount of uranium, relatively speaking. It's actually somewhat of an abundant natural resource for us. China, it's not a natural resource for China. They have to import their uranium. It's just not a natural resource for them. Australia is loaded, but they have no nuclear power plants, which we always kind of find interesting. But you can kind of see Canada has there's a lot of Canadian mining, uranium mining out of Canada. So there's a lot of places around the world where you can successfully mine uranium and then utilize it for civilian power production. A little bit of a complex chart here, but I'll just kind of walk you around the circle. So after the uranium is mined, there are a number of chemical processes that convert it into a form that can allow it to be enriched. Remember, it's naturally a little less than 1%. It has to be enriched to like 5%. And then it's put in the form of powder. It actually looks like dirt. I know nobody likes it when I say that, but it literally looks like dirt. I mean, it looks like fine topsoil, but it's much more dense than dirt. It's quite dense. It's a granular kind of powder, and that's used to fabricate small fuel pellets, which then go into a fuel bundle, which I'll show in a minute, which goes into the power plant, and it'll run for a number of years, and then eventually go to a spent fuel storage, or perhaps one day what we're proposing, we'd like to propose are some recycling capabilities for spent fuel, which would really help. So to close the fuel cycle. Right now we stop here. We really don't close the fuel cycle, so it's not really a cycle yet. But we would like to get to the point where we can close that fuel cycle and then recycle and recover the remaining nuclear fuel and then put it back in the cycle. So it's not completely a cycle, but it's something we want to work toward in our industry. So again, I kind of talked about this already. Different types of mining, open pit uranium mining. You'll see a lot of these out west in Wyoming. Large number of open pit mines. Underground mining is big. That's what it looks like when it comes out of the ground. Kind of cool. Have you ever seen it? Pretty neat. Again, slightly radioactive. So if you were to take a small Geiger counter and put it up to this, you get a few low level clicks. It's just slightly radioactive. And then it gets converted chemically into a yellow cake or a yellow powder, which is then converted to, which has then gone through a pretty complex chemical process to get it into the form of a gas. Now, why do we want it in the form of a gas, uranium hexafluoride? That's the form that it's very easy to enrich. When it's in the form of a gas, it's very easy to enrich. It's probably one of the easiest ways to enrich it. So we get it into a gas, enrich it, and then deconvert it back to a powder or reconvert it back to a powder. So it's got actually some pretty complex chemical processes. The ultimate product is uranium dioxide, which is this brown dirt-like powder that I said. And it will be formed into these small little pellets. Pellets are about the size of an eraser on a pencil, maybe a little bigger. And there's a number of really good physical material properties for uranium dioxide that make it really good as a nuclear fuel. Has great thermal conductivity, good mechanical properties, and it helps it to be a very robust thermal mechanical fuel for the nuclear plants. And pellets get loaded into the rod. Rod goes into a big fuel bundle. Bundles are about 12, 13 feet high. They're quite heavy. They weigh several hundred pounds. And then hundreds of these get loaded into this region inside what's called the core of the reactor. Some of the small plants have just maybe a few hundred bundles. Some of the larger ones can have up to 1,000 bundles. There's a big plant. And so the fuel assemblies get loaded in the core. And then the core is where the heating of the water takes place. And then the steam goes out the top through a series of dryers and separators. So it's, as my mom likes to say, it's just a fancy way to boil water, isn't it? And she's right, it is a fancy way to boil water, but that's exactly what we're doing. We're boiling water. But it's very, very concentrated energy source. So you can produce a lot of power with this. Again, this is kind of the process of fission, as I mentioned earlier. Neutrons have to be slowed down after they're emitted so that they can be capable of producing fission in other uranium atoms. And so the idea here is if you can get a collection of uranium atoms close enough and slow the neutrons down, you can get a chain reaction that sustains itself through a combination of uranium and other types of materials. You can have a self-sustaining chain reaction. It is quite different than a chemical source of heat. And so some of these differences are important to talk about. So when you look at what goes on in a nuclear chain reaction, everything of interest happens at the nuclear level, at the subatomic level in the nucleus, as compared to, let's say, chemical heat source, which is a combustion reaction, which deals with the electrons on the outside of the nucleus. Everything happens for us in nuclear inside the nucleus. No ignition source is needed. That's an interesting one. So if you have a combustion source, you have to provide, if you have a combustion process, you have to provide an ignition source to initiate the combustion reaction. We actually don't need that for nuclear. This process of fission will run by itself without an ignition source. So you have to be very careful how you handle this material, because you don't want this chain reaction running when you are not ready for it to run. So you want to make sure it's contained and controlled very carefully. In a chemical reaction, you just remove the ignition source and the process stops. For nuclear sources, we remove the neutrons. And if you remove the neutrons, there's nothing to cause more fission, the chain reaction stops. So we control the nuclear chain reaction by removing neutrons from the system with things that are called control rods or control rod absorbers that are inserted to actually capture those neutrons, but not fission. And if you get the control rods in a certain place, in a certain location, they can balance, the absorption there can balance the fissioning that's happening, and you can have a self-sustaining chain reaction. And if you want to shut the reaction down, you just insert all the control rods and the whole chain reaction stops. So that's the basic principle behind how that works. As I said, very, very concentrated source of power. So one of those little eraser size uranium pellets packs a tremendous amount of energy. The equivalent of about 1 ton of coal, about 150 gallons of oil, a lot, right? And so significant energy source, which is one of the reasons why we think it really has to have a place here in the energy discussion for the future. Couple of interesting features that are important to keep in mind is that once the nuclear chain reaction is shut down, there is still a lot of residual heat left in the reactor because of those fission products that I mentioned earlier. They still contain a lot of kinetic energy. So those radioactive byproducts produce decay heat, which is not insignificant. It's about 6–7% of the full rated power initially, and then it slowly decays over time. So for a nuclear power plant, you got to make sure you maintain cooling even after shutdown, because there's still a fair amount of residual heat left in that fuel for several months until after it decays enough to where it's not significant. And as I said before, a high concentration of energy. This is a schematic that kind of shows some of the barriers of protection that we have for a typical power plant in the US. So the pellet itself is actually one of the barriers because it traps all those fission products. Outside the fuel pellet in that cladding material is a tube made of zirconium alloy. That is a boundary. In case fission product gases were to escape, they would get caught in that gap in between the pellet and the clad. And so the cladding is a boundary. Then you got the reactor itself, which is a pressure boundary that were the fuel to melt under a severe accident condition, you would get all of the fission products trapped inside that very, very thick stainless steel vessel. And then outside that vessel, you've got a very large concrete reinforced containment structure, several feet thick of concrete, reinforced concrete, that is capable of holding a significant amount of fission products and energy and gas. And then finally, the reactor building itself, which is also operated at a negative pressure, so that if anything were to leak out, or anything were to leak, it would stay inside the building. So you've got no less than 5 barriers of protection, keeping that fuel safe and keeping the fission products safe inside that reactor core. And so because of this, in the US, we've never had any significant release of fission products, because even in 3 Mile Island, when the fuel melted, pretty much everything stayed inside the vessel and inside the containment. So nothing significant escaped outside of that. So very, very important that we have in the US these pressure boundaries that keep the fission product gases trapped and safe in the rare event of a fuel failure. Couple of the main types of power plants in the US that we'll see. One is called the pressurized water reactor. That's the one on the left. And then the boiling water reactor is the one on the right. The boiling water is simpler in that you're boiling the water inside the reactor vessel and sending the steam right to the turbine to spin a generator and then produce electricity. Pressurized water reactor has a second loop. So you're not boiling the water in the reactor core. It's actually under much higher pressure. And then it goes to a steam generator, which then produces the steam through another loop. And then that steam goes to the turbine generator. So 2 loops on the PWR, one loop on the BWR. The BWR, the boiling water reactor, is sometimes referred to as a direct boiler, because you're boiling directly from the nuclear fuel. Pressurized water reactor, everything stays as a liquid, essentially stays as a liquid in the main primary system, and all the boiling happens in the steam generator. But the trade-off is you have to operate at a much higher pressure than you do for a direct boiler. So there's some trade-offs. But those are the 2 primary designs we have in the US. About 2/3 of the US reactors are of this PWR type, and about 1/3 of the BWR type. And that's what we see here in the US. Nuclear has a fantastic track record of capacity factor. Capacity factor means what percentage of the time that you are able to run are you actually running? And nuclear, I mean, hands down, beats every energy source there is in terms of capacity factor. The reason for this is because throughout their history, whenever a nuclear plant shuts down to go through, let's say, a refueling outage or a maintenance outage, it costs a lot of money. And so we've gotten really good at optimizing outages, refueling, and getting the plant back online within like just a few weeks. Used to be plants would be shut down for months and months at a time. Today, if a plant is shut down more than a few weeks, it's out of the ordinary. So nuclear has really improved its capacity factor over the last 20 or 30 years, where these things are running 24/7 for years at a time. And the only outages are planned outages to do a refueling. So we've gotten really good at our capacity factor, being able to stay online as an active source. So obviously wind and solar can't really compete there because the wind doesn't blow 24/7. The sun doesn't shine 24/7. So we think nuclear offers a real advantage to other energy sources in that we can be a reliable baseload capacity at times when some of the other sources maybe can't produce or aren't able to produce enough electricity. But of course, with that comes the question of, well, what are we going to do with all the nuclear waste, right? Because we got all this spent nuclear fuel, and what do we do with that? Most of the spent fuel today is stored in spent fuel pools. Some of the older spent fuel is actually stored above ground in a dry cask storage. The radioactivity levels have decayed and the heat loads have decayed enough that they're not very significant. They can just be air cooled. So they're not really that large a risk. They have to stay in a shielded cavity though. But one of the things that surprises people is that the volume of waste for nuclear is actually incredibly small. So when you look at the volume of waste in terms of amount of waste that's generated per year for nuclear, it is a fraction of the waste volume for other municipal type sources. And if you normalize it to the nuclear is the normalizing factor, and you normalize it to nuclear, you can tell, I mean, even human waste has 100,000 times the volume of nuclear waste. We're a very, very small volume of waste. All of that waste is contained in those fuel pellets inside that bundle, which is not a very large volume, relatively speaking, compared to other types of waste sources. If you could take the fuel from every nuclear plant in the United States and store it in a building, and it would fit on the football field of Carter Finley Stadium. That would be the size of the storage facility. You could put all of it in one size building that would fit on a football field. So it's really not that much in terms of volume. In terms of, now, of course, it's quite radioactive. It would need to be shielded, but by volume size, it's really pretty minimal. And so that's one of the reasons why we think that going to the next step for recycling and reprocessing has to be looked at very carefully. Because even though the volume is small, there's still a lot of radioactive material that's in that fuel that has to be handled safely. And so we proposed a number of different types of options for recycling and reprocessing. Again, these are things that we're looking at for the future to be able to recover the usable fuel that's still left, the usable nuclear fuel that's still left, and then what we would send to a geologic repository would be a fraction of the volume that we have today, even though the volume is not very large. Okay, so that's kind of it for, oops, wrong way, sorry. For the current state of nuclear. Any questions on sort of that pretty high level view of nuclear and where we are today? Okay, we're getting there. Let's see. I don't want to run too late. So next gen nuclear. This is where people get kind of excited because there's a lot of cool stuff going on right now. So starting in the 1950s, we were at what we now call generation 1, first generation nuclear. And these were some of the things I talked about on my timeline a little while ago. We are rapidly moving toward what we call now generation 4 or Gen 4, which are the advanced reactor technologies. We are really in this space right here. We're really in the Gen 3 plus stage right now, but we are rapidly moving toward the Gen 4 stage, which are the next generation advanced reactors that have a lot of really interesting features and capabilities. Right now, the Department of Energy is funding no less than like a dozen projects for next gen advanced reactors. And some of this stuff is so cool that I just marvel at some of the things that are going on right now. And so there are a number of projects that are being funded at research labs, private companies, a lot of cost sharing projects where the government is partnering with commercial industry to say, hey, we'll put in half if you put in half to help you develop your next gen advanced reactor. And so there are a number of really interesting projects. The DoD is actually wanting to put a small nuclear reactor inside a transportable truck and drive it around. That's one of their projects for a next gen advanced micro reactor. A number of projects for a molten chloride reactor, sodium fast reactors, molten salt reactors, all kinds of really interesting next generation advanced reactors. High temperature gas reactor, that's what X Energy is working on. So a lot of really exciting things here that are coming in this next decade for nuclear. So if you ever wanted to think about going into nuclear, now is the time to do it. Because I mean, I have never seen it like this in my 36 years in this industry. There is just so much going on right now for next gen, Gen 4 advanced reactor technology. It's just really interesting, some of the concepts that are being considered. And this doesn't cover all of them, there's a whole nother timeline here that I didn't put on here for space reactors, like using nuclear reactors for space propulsion, right? Because if you're going to travel to Mars, you know, you can't run out of fuel halfway there, right? So, and there's no place to stop for gas on the way to Mars, right? So, yeah, I mean, nuclear power has really good capability for deep space exploration as well, which again isn't even on here. This is all commercial civilian applications that are going to be for this power, the land-based nuclear power industry. Some of the things we're seeing as well are some of these advances in fuel. One of the more interesting ones is TRISO fuel, the tristructural isotropic fuel, that really is composed of these small kernels. So rather than a pellet, it's actually an encapsulated kernel of uranium dioxide or oxycarbide that is incredibly robust and can tolerate significant temperatures. This fuel is used in high temperature reactors. It is fuel proliferates. It is fuel damage resistant and accident tolerant, which means even under a complete loss of cooling event, it won't melt. It can tolerate extreme temperatures, and it's basically accident resistant fuel. And so we're starting to see, as the industry is moving toward this passive inherent safety, we're seeing it for the plants, for the fuel types that are used, to really give a lot of robust safety considerations for these plants. And also wanting at the same time to be able to have them be very efficient and cost effective. So, okay, so how am I doing on time? I didn't go too far, did I? Still got a few minutes. Okay, questions, comments, any thoughts or comments? I know I went through that pretty fast. Yeah.
I want to ask about, I don't have the data, but I think most of the people fear about the radioactivity of the waste. So is there technology or innovation developed to reduce the radioactivity of the waste, maybe make it bond with some elements or something?
Yep. So that would be this right here. Oop, went too far. These types of integrated facilities for spent fuel processing are really what are on the table for the future, which will significantly reduce the amount of fission products and actinide waste. So yeah, I think this is how the direction the industry is looking at to do that. Yeah.
In relation to the waste, would microreactors like produce less waste in proportion to like the bigger scale?
So proportionally, they would be the same, but the total amount would be smaller because a lot of these reactors, let me show you this, are significantly smaller than the power plants we have today. So one of the interesting things that happened in the industry was in the early days, we had small reactors and they were like, hey, this is really cool. Let's make some big reactors. And so everything went big in the 70s and 80s and 90s. Well, we're actually going the other way now. Things are getting smaller because what we're seeing is that you can deploy these smaller reactors much more cost effectively. And if you want more power, just add another unit, add 2 units, add 3 units, right? Buy 2, buy 3, rather than having one enormous power plant. So yeah, the spent fuel composition is smaller because the plants are smaller. But of course, if you deploy more units, then you'll have more fuel, right? So, but that's kind of the direction that the technology is going in now. So a lot of these advanced reactors are, rather than being thousands of megawatts, they're on the order of like hundreds of megawatts, a good order of magnitude or so less. But again, that's for economics and for safety reasons. Yeah.
Sir, on your slide that showed all the different levels of encasement,
Mhm.
so go back to that.
Yeah. Oops. Yeah.
So you said that the reactor in Chernobyl was missing some of this.
Yeah.
What it didn't have.
So it didn't have this 4-foot thick concrete wall pressure boundary, did not have a containment. All it had was the building, which was basically just a steel structure, like a warehouse kind of building. So it did not have containment. It did have a vessel, but it was not a pressure vessel. So it wasn't as thick as our pressure vessels are. And the fuel type also was different. So it was missing at least 2 of those boundaries.
Okay, and then next question, for 3 Mile Island, you described that basically the radiation was kept in the concrete. What do you do with it then?
So they had gone through a number of years of cleanup activity to get that waste cleaned up, the components decontaminated and then sent to a waste disposal site out west. So, yeah, the 3 Mile Island plant was not usable, that unit 3 was not usable after that event because of the damage that happened.
Okay.
So, yeah, it took a while. It took like 12 years, I think, to clean it up. It was a big deal. It takes time. That's why you don't ever want to let these things happen. You want to put all your effort in and never letting it get there. Because you got a big problem to deal with it afterwards, if it does, because you got a lot of cleanup effort after that. So it's a good question. Yeah.
I wonder if like public perception and kind of misconceptions about nuclear energy,
Yep.
is that still kind of a major barrier to growth in the area, or are you noticing like
So,
a shift out of?
Yeah, I will tell you. So I'm noticing two things. One is this generation is way more pro-nuclear than any generation I've ever seen. And I can only attribute that to one of two things. Either they maybe have lived during a time period that they were not around during the 3 Mile Island Chernobyl days. And so those are kind of like past history events to them. And secondly, they are far more concerned about climate change issues than the previous generations, which is really good. And so to me, those two things, I have seen students that I've interviewed and talked to who are very pro-nuclear, and not just the people who know about nuclear. Like, I would expect nuclear people to be pro-nuclear, but even people that aren't necessarily very knowledgeable about nuclear see that, but you know what, we need to really focus on giving this technology a chance and doing it right. And so, yeah, the public perception is starting to change. It's fascinating to see. But as someone who's been in the industry 35 years, I've never been more encouraged by what I'm seeing. So yeah, I think it's great. I think this next generation is going to really do some great stuff with this technology. I may not be around to see it, but that's okay. I'm glad it's going to happen because I think the time has come. So, but yeah, public perception has really shifted in the last 15, 20 years. And I think it's probably driven by a lot of those factors. So yeah, interesting, really interesting. Good, yeah. Yeah.
Can you talk a little about the, I guess, you see on the news a lot about the Russia, Ukraine, that one power plant that is kind of in the area of the conflict. Can you talk about, like, it's all guys like the CNN sound bites. What is that? Is it a really big deal?
Yeah, I mean, okay, so it's actually 6 power plants at that station. So it is one site, but it contains 6 full-scale power plants. So it's a lot. There's a lot of power that's being produced there. Yeah, I mean, we don't design nuclear plants to operate in a war zone. Yeah, that's not one of our design criteria. So that's a concern. And for anybody who works in nuclear, when we saw what was happening, we were kind of like, wow, that could be a problem if things were to go wrong. Fortunately, as you pointed out, or we were talking about a moment ago, the robust design of these power plants is such that the newer ones and the ones that you're talking about are closer to these designs than Chernobyl. They do have pretty robust infrastructure, but still, they weren't designed to, tolerate a missile strike, right? So there is a little bit of a concern there about what may happen with them. I think ideally it would probably be safe to just shut them down until the conflict is resolved. Don't know if that's possible, but yeah, it is a little bit of a concern.
So if you did just turn it off, like how long until it's like safe to keep on? That's a really
Yeah. No, it's a good question. I mean,
if we just put the switch today.
yeah, it would take several months for everything to decay and cool off to the point where it would not be as significant a threat. But you got to realize there's probably still spent fuel at that site, like most power plants. So there's still a risk, right? There's still a risk. So yeah, unfortunately, that's a difficult situation right now. But yeah, it's got a lot of our attention for sure.
To assuage some anguish, wouldn't it be more akin to Fukushima release of radionuclides? It wouldn't be a Chernobyl.
No, it would
That
not.
would be like a small amount due to the way that LWRs.
Yeah, it would certainly be less, but again, even any release is not good, right? We want to minimize any. But yeah, it's still, there still could be a risk. So, yeah, unfortunately. Okay, good. Any other questions? Yeah.
Continuing about the waste of the nuclear reactor, you already talked about what's and how what to do with the waste in the future. But
Yes.
what about the waste in the past? Can we clean it or?
No, and so
Is
this,
there a-
yeah, so this right here is actually, I think I'm going the wrong way. So this is for the waste in the past. Right, so this would take advantage of spent fuel. See this, the spent fuel? So this would be spent fuel that's already being stored at existing power plants. Yeah, so it would be reprocessing, recycling all of the existing spent fuel.
Can it be like, maybe I don't know in the future, safely dumped in the future? I mean, like, are there physical limits? So, okay, we cannot do that.
Yeah, it could, once it goes through this process, you could have a small amount of remaining waste go to a geologic repository. Right now, it cannot in its current condition. So it has to be just stored for now, but eventually it could go. The remaining waste could go there.
So geologic repository means put it in a cave or just?
Yeah, yeah, in a large reinforced container inside. I don't know if you've heard of Yucca Mountain. Maybe you had heard about Yucca Mountain. That was supposed to be the long-term repository. Unfortunately, it hasn't really gone as planned, but that would be the ultimate repository.
I mean, like, can we eliminate the geologic repository? I mean, like, or is it physically impossible?
Well, it would be, I mean, you're always going to have a little bit of residual waste left over. But again, the volume is so very small. Again, even the volume today is very small compared to other waste. That I think that's something that can be managed pretty safely, you know, far away and in a safe, location. Yeah.
I don't know, do you think that'll be possible to like reach like energy, that's like clean energy 100% without nuclear sources? Because like,
Yeah.
like now everybody's saying like we're gonna move to like 100% like carbon-free emissions.
Yeah.
It
Well,
seems kind of hard without nuclear.
yeah. So I would say, I mean, here, let's just go back to this for a second, because this is a good discussion point. So we got to be careful. Even, I mean, when you look at, let's just take solar, for example. Yes, it produces carbon-free electricity, but where do we get the solar panels from? Like, do they just fall out of the sky and they land in our backyard? No, there's a tremendous amount of chemical processing and material processing that goes on to make these super duper solar panels. Nothing is carbon neutral, ultimately, right? Wind, you know what it takes to create wind turbines? Wow, a big job, right? So yeah, but you know what? Nuclear too. We have to mine our uranium out of the ground. You got to do that with trucks and large heavy equipment. Everything has some carbon impact. Nothing is truly carbon neutral, right? So every one of these has a carbon footprint of some type. Now, the goal here is to minimize. So yeah, I think we can get to a very low levels, but I don't know if we'll ever get to zero because everything is going to have some impact. But we have to get to the point where it's sustainable, where it isn't causing a threat to our existence, right? But yeah, I don't know that we'll ever get to that perfect energy source. Everything, it's hard to get something from nothing, right? So, but I think when you compare it to all the other energy sources, I think, nuclear plays quite well with the rest of them. But yeah, it's a good question. It's definitely a good question. Yeah, I don't like to remind my Tesla owning friends that while you're driving around in a car that produces no CO2, almost half of the energy in the United States is produced from coal. So like 1 out of every 2 Teslas is basically powered by coal. That's kind of what it means, right? So we got to get here. We've got to get here where wind and solar and hydro and nuclear, geothermal, where those are the things putting all the energy on the grid. Again, it's not zero, but it's much lower. That's gotta be the goal. And then we can all drive around in electric cars. That'd be awesome. But I mean, think about that. Think about how much of the electricity demand is gonna go up when every car on the road has to be in a garage charging at night. Right? That's a lot of electricity we don't have right now. So, yeah, we're gonna need some sustainable energy to do those kind of things. And they need to be done, but it's gonna take an effort for sure, so. Good, any other questions? Good questions. Yeah,
I know US has so many nuclear missile war. I don't know why it is so many, but can it just be repurpose the nuclear in the weapon to fuel for
believe it or not, that's a great question. There was actually a program about 25 years ago to do just that. At the end of the Cold War, there was a large amount of weapons material that was going to be converted and blended to make mixed oxide fuel, uranium plutonium oxide fuel. Unfortunately, the project didn't go much farther than the first initial stages. We did partially build a facility at a DOE site to do that, but there was a plan. It was called metric tons to megawatts or something, where they were converting all that large metric tons of plutonium into mixed oxide fuel for power plants. So yeah, that was something that was being planned. And we haven't gotten there yet, but it was still something that was being looked at. Good question. You've done your homework, I can tell. Okay, all right. I don't want to go much longer. I know everybody has class or something to get to. Thank you so much.
Thank y'all for coming. Hey, they came here to see him speak, not me.
Energy Week is still going on. Check out go.ntp.edu.